Good morning. I am going to explain how we create our excitation tables. So, why are the excitation tables important? Well, we need our excitation tables to be able to create the present state, next state transition table. Without it, we're unable to do that. And to create the excitation tables, we have to derive this from the characteristic table. And that table is derived from the truth table. So in this video, we are going to take you through the steps in completing the derivation of the excitation table. So in this example, I'm just going to go over the K flip-flops with you as quickly as I possibly can. So first, we look at the truth table. Again, we see with the clock is again a form of an input. So you see when it's 0, it doesn't matter what J or K is, it will always be the present state. The circuit is off. It is, well, not off, but it is not gonna it's not gonna change state. It's only gonna change state on the up when the counter clock goes to high. When it's 1, basically, that's when it's going to change states. So we look here and we see when J is 0, K is 0, the inputs, then the next state, this is what Qn plus 1 is, this is the next state, is equal to the present state, which is Qn. Alright, now we see when J is 0, K is 1, the next state will be equal to 0. Then we see when J is 1, K is 0, the next state will be equal to 1. And when J is 1, K is 1, the next state will be equal to whatever the present state is not. So again, if the present state is 0, then it will go to 1. If the present state is 1, then it will go to 0. That's what the next state will be for JK. That is the truth table. Now, we use this table to figure out what the characteristic table is. So, again, we go through the logic using the truth table. We see that the present state is 0, and the inputs are J and K. What is the next state? So when the present state is 0, and J is 0, K is 0, the next state is 0, just as we see here. Here. It's going to be whatever the present state is once J is 0, K is 0. So that's it here. When J is 0, K is 1, once more we see here and here, it's going to be 0 right here. And the same thing here. When J is 1, K is 0, it's going to be 1, as we see right here. J is 1, K is 0, it will be equal to 1. Now, when you see J is 1, K is 1, we see the present state is 0, and the next state will be 1, which is exactly what we see in the truth table. When J is 1, K is 1, the next state will be whatever the present state is not. So once again, this follows. And again, this is what will happen for the second half. When J is 0, K is 0, whatever the present state is according to this will be what the next state is. So here, present state is 1, next state will be 1 as well. And once again, when J is 0, K is 1, it'll be 0. When J is 1, K is 0, it'll be 1, just as we see in the truth table here. And finally, when both inputs are 1, the present state, and the present state is 1, then the next state will be 0. Once again, the exact same thing we see in the truth table. So this is our characteristics table. Alright, once again, we are going to use the characteristic table to create our excitation table. Alright, so for the excitation table, again, this is where we just figure out what are the inputs needed so that our present states can turn to the next state. Alright, so we're going to go to the first one. In the present state is 0, next state is 0, which we will see here. When this is 0, this is 0. What is J? J is 0. Once again, we see it here. When the present state is 0, next state is 0. j is equal to 0. So it's 0 in both cases, so we can say that j needs to be 0. Alright, now we're going to look at k. When present state is 0, next state is 0. In this case, it'll be 0. But when the present state is 0 here, next state is 0 here, we can say that it can be 1 as well. So what does that mean? That means we can see both 0 and 1 being input values to create this. So this is where we have the x. This is why I should say we have the x here. The x represents a don't care. This is because it doesn't matter whether it's 0 or 1. It is not influencing whether the output will be. It doesn't influence the output, what the next output will be. This is basically what it is. So we put an x in this here as don't care. So that is the case. We're going to go to the second example. We see present state is 0, next state is 1. So these are these two sections here. And the present state is 0, next state is 1. We see that j is 1 here. And we see when the present state is 0, next state is 1, j is also 1 here. So we can say that j has to be 1 in order for this to happen. So that's why we place 1 here. And then we look at k. We see when it is 0 and next state is 1, k is 0. But we also see once again that when the present state is 0, next state is 1. Oops, looks like my laptop's going to die soon. Then we see that this is going to be, k is going to be 1. So once more we can say that this is going to be a don't care situation. Now we can obviously imply that the rest of these, we can fill out the rest of the table using this logic, and this is what the final excitation will be. Final excitation table will be. So this is how you derive your excitation tables for the different types of flip-flops.